Welcome to the first lesson in AP Calculus BC, or perhaps you're a few lessons in AP Calculus AB. Either way, we're looking at Chapter 0, which is a preview or a review of things that we've covered, some more than others. This is one of those topics that we touched on a little bit, but we didn't do much of. And we will do some of it in calculus, not a ton, and mostly like none of the hard stuff for quite a while. But we're still going to take a look and recap this a little bit. So we're going to be looking at parametric equations today. Now, a parametric equation is going to be an equation which takes the relation between the x value and the y value, and it defines both of those by a third variable, a new parameter, which is called t. And again, that's used to describe both x and y. An example of a parametric equation would be something like this. We have x equals t squared, y equals t, and then t, we get a range for that t variable a lot of times. And so t is going from -1 to 4. So one of the things we could do with this, if we wanted to graph it, because we don't know exactly what this looks like, is we can just make a table. So when you make a table here, you're going to have 3 columns, 4 columns, because you're going to have your t, your x, your y, and then I guess that 4th column would just be the point, which is xy, which is already given. So t, well, we go from -1 to 4, kind of obvious. Let's go -1, 0, 1, 2, 3, 4. It's not always that nice and neat, but if it's something where you're going to be making a table, it usually is. Then we just plug these values into each of them. So x is going to be t squared. Well, -1 squared is 1. And we can just go down. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. And then y, well, y is just t, so -1, 0, 1, 2, 3, 4. So our ordered pairs, we're going to have 1, -1, 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. We can graph these points. Let's start out. Let's see. We have mostly positive y values, all positive x values. Let's put our axis there. And then we can graph. So we have the point 1, -1. Yeah, we can use those 1, -1. It's going to be right down there. I can't seem to hit it. 0, 0. It's right here. 1, 1. Make a point. 4, 2. So we can go over 4, up 2. 9, 3. You go over 9 up 3. It's about there. My other point just disappeared. What? This doesn't happen on a chalkboard. And 14 or 16, 4. It's going to be right around this area somewhere. So, graphing that, it would probably be reasonable that the curve is going to be smooth. It's not going to be a whole bunch of straight line segments, because if we plugged in some in the middle, it would give us things that would smooth it out. And so what we have here is we have a sideways parabola, but not a full thing, only going from this point to this point. So it's a chunk of a sideways parabola, which would be part of a like a square root function. a lot of times with this extra little tail down here at the bottom. And we can actually see what that is. We could turn this back into Cartesian coordinates. Cartesian coordinates are what we're used to using, the XY coordinates. It's actually how we graph this using points. Sometimes it's rectangular. It's Cartesian for René Descartes. So to do this, to change this back, we would take a look at these. We have x equals t squared, y equals t squared. Well, if we could get those both to equal the same thing, then we can just set them equal to each other. That same thing would be t. We're going to make both of these equal t. For this one, we take the square root. So we have the square root of x equals t. But when we take the square root of both sides, we never just have the square root. We have plus or minus the square root of x equals t. And y equals t, which if this equals t and this equals t, that means that y would have to equal plus or minus the square root of x. But only when x, we have to go from there to there. So we can plug in -1 into t, so we get x equals 1. So from x equals 1, which is less than, we can plug in 4. 4 squared is 16. So we get plus or minus the square root of those. Now this would give us both chunks. That's an issue with the square root and stuff like that. We don't actually have both chunks, so it's lying to us a little bit. Sometimes we have to deal with that. You shouldn't have to worry about that. This is kind of a weird example that I picked. But that's how you would put it back into rectangular coordinates. You would set both equations equal to t, put them together, and then see what happens. To graph it, we made a table. Now you can get some pretty crazy graphs with parametric equations. They do awesome stuff. In fact, the title slide, the one that we had before this, with all those crazy circles, that was graphed using a parametric equation. Not a nice parametric equation, but it was a parametric equation. So the definition of parametric equation and parametric curve. So x and y are given as functions, f of t, y of t. That's what we had over here. They were both given as functions. And so the graph is going to be the set of all points, x, y, where it's x of t, comma, y of t, where t is this other variable. Same thing that we just found. And a lot of times, again, the range for t is defined. It's not always defined, but a lot of times it is. So things we can graph with parametric equations really easily: circles and ellipses. So the equation for a circle, parametrically, is x equals a cosine t, y equals a sine t. Now that should make a little bit of sense. If we remember back to our trig, cosine was the x part of the circle, y was the sine part of the circle. This number in front is going to be a stretch, so they're both the same, which means it's stretched the same way. That'll give us a circle. We can graph this by hand. We don't usually graph parametric equations by hand. We usually use technology. If you remember how to do this, and you have a graphing calculator at your house, great. Use your graphing calculator, set the mode to parametric. It'll change it to x equals y equals, and you can do a lot of these things. If you don't either have a graphing calculator or remember, in our Google Meet, we're going to use Desmos again, and we're going to see how we can graph parametric equations and kind of play around with them a bit. So you can just kind of hold on, and I will show you how to do that, just not right in this video. But to show that these are a circle, to change it back into a rectangular or Cartesian coordinate, let's remember that the equation for a circle was x squared plus y squared equals r squared. All right, well, I have x and I have y. Let's square them. So here, x squared will equal a squared cosine squared t, because we have to square both pieces. Y squared will equal a squared sine t squared, sine squared t. Well, I need to add x squared plus y squared. So x squared plus y squared should equal what x equals plus what y equals. A squared cosine squared t plus a squared sine squared t. Hey, look, these guys both have a squared. Let's factor out the a squared. X squared plus y squared equals a squared cosine squared t plus sine squared t. Cosine squared t plus sine squared t. Man, that sounds a lot like something that we drilled for quite a while in pre-calculus. Oh, that's right. That's that Pythagorean identity. What does cosine squared plus sine squared equal? It equals 1. Thus, x squared plus y squared equals a squared. So this a would be the radius of the circle, would be r. So in a circle, this number in front of both of those gives you the radius. Knowing that, we could graph it without having to plot points, if we see that. How about ellipses? Ellipses are very similar to circles, except remember the radius is underneath. We have x squared over a squared plus y squared over b squared equals 1. All right, well, let's see what we have here. An ellipse, it'll be x equals a cosine t, y equals b sine t. So we still have x is with the cosine and y is with the sine, which again makes sense because those are the x and y coordinates in a unit circle. That's what they represent. But now we have the a and the b are different. Well, thinking back to the circle, where that number is the radius, wouldn't it make sense that these would be those radii, those radiuses for the horizontal and vertical? It should make sense, and it will. We'll do the same thing, except here, if we just square them both, we're going to have an a squared cosine t and a b squared sine t. We're not going to be able to factor anything out. But if we remember our ellipse equation, we don't need x equals a. We can have that division. So let's divide first. X over a equals cosine t. Y over b equals sine t. Now we can square both of them. X squared over a squared equals cosine squared t. Y squared over b squared equals sine squared t. Add them together. X squared over a squared plus y squared over b squared equals cosine squared t plus sine squared t. There's that Pythagorean identity again. X squared over a squared plus y squared over b squared equals 1. That's an ellipse, and exactly like what we may have expected from our radii. So the circles and ellipses work out really easily. Now, when you start changing little things in them, like let's say instead of a t, we make it a 2t, only on one of them, that's when things start getting a little bit interesting. And that's something where playing around with graphs, like we're going to do in our Google Meet, can be hugely beneficial because you can see what these changes will do without having to put a whole lot of effort into it. Notice in both of these, the range of the t's went from 0 to 2 pi. That makes one full circle, right? Because 2 pi is a full circle. If we did not limit t, we would just keep going around and around and around in a circle. It would just trace over it more and more and more. If we went from 0 to pi, we would get half a circle. If we went from 0 to negative pi, or negative pi to 0, we would get the other half of the circle. If we went from pi to 2 pi, we'd get the other half of the circle. So that domain can be important. And generally speaking, what it tells you to put for a domain is what will make it just trace it one time. So without having to keep going around, around, around. Lastly, we have lines and other curves. We'll look at other curves when we're graphing, but lines we can look at. So lines, x and y just both have to have a linear relationship to each other, or to t. Because if they have a linear relationship to t, that means they'll have a linear relationship to each other. So, and the way we'd find the equation of a line is the exact same thing that we did in the beginning. We're going to get t equals, it's just t equals something in both of them. Then we can set those equal to each other. So as opposed to doing it with all the variables, let's switch. We have x equals 2t and y equals 3 plus 7t. And then t goes from 0 to 1. So the first thing, we're going to get t by itself. So here we can divide by 2. X over 2 equals t. Here we can subtract 3 and divide by 7. Y minus 3 over 7 equals t. The t's are together, so we can put them together, or we can set them equal. X over 2 equals y minus 3 over 7. Well, our lines, we like to have y equals, so let's get y equals. Let's multiply by 7. So we have 7x over 2 equals y minus 3. Add 3. Y equals 7 halves x plus 3. That's an equation of a line. However, we have a domain restriction on t. This effectively makes it a line segment. So you can draw a line segment because it only goes from when t equals 0 to t equals 1. Just like we did in the beginning, let's plug it in for x. This time we won't have the issue with the whole square root of a negative. So we plug it into x. If we plug in 0, we get 0. So it'll be 0 is less than or equal to x, which is less than or equal to, plug in 1, and we get 2. So it'll be from 0 to 2. So if we wanted to graph this, I didn't put a graph on this page because it was just a line. If we plug in 0, we get y equals 3. And if we plug in 2, we get 7 plus 3 is 10. I don't know how far up that went. But we get somewhere right in there. And then you just connect the dots using a straighter line than I did. And there we go. So that's all we're really looking at with parametric curves. You're going to be changing them to rectangular, just like we did a few times. You're going to be identifying, looking at viewing windows, stuff like that. Again, if you remember that, awesome. If not, we'll take a look at that while we are looking at a graphing calculator, because that will help a lot. So I will see you in our Google Meet, but until then, keep working problems, keep asking questions, and as always, happy mathing.